So welcome back and welcome to the last formal lecture in this course on quantum computing and quantum machine learning. And the topic today is actually first to go back a little bit to what we did last week in connection with quantum support vector machines and in particular quantum neural networks, because this is a method which we just started to scratch the surface last time. And in a way, this set of lectures on quantum machine learning require in a certain sense that you have some background in machine learning, because I will not have time to go through the classical. I did that with quantum support vector machines, but with quantum neural networks, I'm going in a way to assume that you have a kind of overarching view on it. And essentially what you have then is a method where you update the parameters by the algorithm which is called backpropagation. And this backpropagation algorithm is actually nothing but you applying the chain rule to a function which evaluates the quality of your model. So one of the typical functions is the mean squared error. So then you calculate the gradients of this function with respect to all the parameters. And the parameters in your case are essentially, in a classical neural network, they are the weights and the so-called biases, which define a neural network. And if you have many hidden layers and many nodes in each layer, you can have hundreds of thousands of parameters. So in principle, it's a multidimensional convex, often convex, we are hoping it's a convex optimization problem, but it's typically a multidimensional optimization problem. Now, when you deal with a quantum neural network, so what we did, we decided to follow a more narrow path. So what we are saying is that we have a classical data set. So this classical data set could be you having, let's say, 4 specific features, 1, 2, 3, 4, which means that you could use, for instance, 2 qubits to encode these 4 possibilities, these 4 features. So you would transform the classical data into quantum data. And this is normally done, there are several ways by doing that, but the most common way to transform your data is to use rotation matrices, which then introduce angles as parameters. So one of the things I wanted to say a little bit about today, besides discussing the codes and the architecture, is a little bit about the way you actually set up a quantum neural network. Now, there is an image here, which is perhaps not the best one, but you could now think of, in this specific case, that you have something which we would call a given number of quantum registers. So this could be qubits, which are used to encode the classical information. So this classical information could be, let's say, the pixels of an image, and you want to run a classification problem. So what you would do then, so this could be then prepared as bits 0, 0, 0 for all of them, and that would define this initial state. Then that initial state is transformed through these different rotations. And one of the examples which we discussed last time was actually to look at these rotations as ways to encode the features of a given data sample. So with features, you could think of something like the example we looked at last time, like the credit card score. And the feature could be the age of the credit card holder. It could be the income of the credit card holder. It could be the occupation of the credit card holder, etc. And that would be the features which you then could, each feature could then be encoded in these angles and rotations. And then, if you want to, you can also entangle the different features to give more complexity to the way you encode the information. Then after some time, so if we go back, so I'm going to jump a little bit back and forth between the slides from last week and the slides from this week, for this week. And one of the things which we went through in quite some detail last time was the so-called way we set up a standard quantum machine learning algorithm. There is one part which is the encoding part, and then we have the processing part, and then we perform the measurement. The encoding part is typically done by this amplitude encoding, where the different angles can then be used to represent features. Now, what you are going to get then is a network which will contain different parameters in terms of these angles. And if we jump back to this one, so you could also have angles which are included in the control gates, which entangle two qubits. But what is pretty common to do actually is to leave the control gates as they are through the whole computation. And then the only parameters which you have, which are going to optimize, would then be the parameters represented by these rotation matrices. Now, this is normally called a parameterized quantum circuit. And if you think back to what we did with the variational quantum eigensolver, this mimics very much what we had there. The variational quantum eigensolver is also a parameterized quantum circuit. And typically what you would end up doing then is that when you perform the measurements here, you could now think of having n registers, and you could have something like m measurement operators. And then the input is typically this quantum state psi of k, which then encodes, let's say, the kth sample of a data set. And then with the m measurement operators, the output is typically a bit string, which then can be encoded up to, since you have m such bits, you can then encode it up to 2 to the power of m integer values. So this is something which gives you the advantage of a quantum computing and quantum machine learning algorithm, the fact that you can encode information into many, many more strings than you could do classically. So for a binary classification problem, for instance, it is normally sufficient to just perform the measurement on a single qubit at a time. And then the measurement produces a single sample. And what you would do then is to repeat these measurements again and again. And then you collect them. And then you look at the fully collected amplitudes and which one of these appear the most. And then you would say this is the most likely outcome. So you would just repeat these measurements exactly as you did with the variational quantum eigensolver. So one way to think of these quantum machine learning algorithms is exactly as we did in terms of the variational quantum eigensolver. So you will often see that when people write textbooks about quantum machine learning algorithms, that the quantum eigensolver, the variational quantum eigensolver, the VQE, often appears together with the standard material about quantum machine learning algorithms. Because what you end up with is a parameterized quantum circuit, a PQC as we called it last time. And what you would typically do is exactly what we did with the variational quantum eigensolver, is that you would run this as the image which you see here, as your quantum algorithm. And then when you perform the measurements, you have updated the parameters theta, which you have here, and the parameters theta would then be fed into the gradient descent method, which runs on a classical computer. And this is exactly what we did in our previous case. Now, there's one thing I wanted to remind you of, and this is essentially the way these calculations are done and what kind of distinctions you would have from this one and the VQE algorithm. So let me try to explain that through the standard whiteboard notes so that we can slow down the pace a little bit and that you hopefully see the basic ingredients. And then when we've gone through some of these basic ingredients, we can again go back to the slides from last week and look at how we would encode the information. So if we just scroll down a little bit, we are going to jump a little bit back and forth between the whiteboard notes and the discussions which we didn't finish last week about the quantum neural networks and how we would set that one up, because these are essentially, they are called often parameterized quantum circuits, or actually variational quantum circuits, because we are going to perform a variational calculation where we update the parameters, and the function which we often are going to optimize is a function which has a well-defined minimum. And this means that we often end up with a lower limit for what we're going to optimize. So let's take a look at a simple example and remind ourselves a little bit about the way we also set up a classical neural network. So let me just set this up here and go through some of the mathematics here. Now, if you think of a training data set, which we have access to, so we would typically have, if we think of a classical machine learning algorithm, so you would have a training set. And this would contain some input variables. So this could be the pixels of an image. And then the training you would like to do in this specific case is to figure out whether the images, which now represent paintings, are Van Gogh paintings or not Van Gogh paintings. So it means that the output which you have then is a set of paintings. So I give you photos of, let's say, 1,000 paintings. And then we have some output, which is now a binary output. So this is often the simplest case, but it serves as a way to understand and follow the basic mathematics. And it's also the easier case. So your output here, the typical output would, in this case, if we look at a single output, y of I for one of the data sets, that could typically be a 0 or 1, true, false. 0 if it's not a Van Gogh, and 1 if it's a Van Gogh painting. If you prefer, you can replace that with Leonardo da Vinci or Michelangelo or whatever. And then you have tons of this. And this is the kind of data set. So this is a binary classification problem. And then you can look at different ways to gauge the quality of the model, because you're going to make a model, and that model is now going to be represented by some function, I, for the specific output you want to find. And this depends on some parameters theta. So in our case, these parameters theta will then be the rotation angles which we set up when we transform the data. So classically, if you think of a neural network, this would just be the parameters of a neural network. And then we have the universal approximation theorem, which says that with a given hidden layer, we can actually approximate a function which is a nonlinear function to a given error. So the universal approximation theorem does not tell us what the error is going to be like, but it simply tells us that this function, suppose now that we take this function, what we could do, we could actually gauge the quality of this function by looking at the number of correct classifications, or you could now think of setting up a loss or cost function, which is given by the mean squared error, where you simply count or look at the difference between all the measurements, the outputs you have, your data set, y of I, minus this f of I as a function of theta and squared. And then your parameters are then obviously optimized by some gradient descent method, which means that we need the gradient of this function c. Say it again. This one? Oh, I should say that sometimes what you would see is that this is a good point, actually. So you often define this is just a function which gauges the quality of your model. And if you put a 1/2 here, when you take the derivative, you get rid of the factor of 2. Sometimes, however, and I normally prefer to actually not set it up like this, but I prefer normally to have it as the mean squared error, which is now an expectation value, a sample expectation value. So you will see in the literature that people will differ a little bit in the way they define it. Sometimes you have 1/n, and sometimes you have 1/2. So as long as you're consistent, I mean, that's the most important thing. Now, if you do that, what you would have then is that this function here becomes simply minus, if you have a half, I equal 1 up to n, and then you obviously have y of I minus f of I of theta, and this is then multiplied with the gradient of f of I of theta. Now, when we do this classically, the function f of I is then something which would depend on the activation functions of the different layers, etc., etc. And it will also be something which depends on all the different layers which we have. So this theta which you have is something which is not dependent only on the final output layer. And this is why you use the back propagation, because in the back propagation, if you have a neural network, where typically you have an input layer here, and this feeds then into, so this will be your input layer, where you feed in your x's. Now this feeds into a set of hidden layers, where you can have as many as you want, as long as you don't overfit. And then you have this feeds out to an output layer. So we just call this for the input. Here it's where you produce your f of I of theta. Now, the typical way by which you do this now is then to use that to compute this quantity. And that quantity receives the final output which you want to reproduce. Now, the back propagation is actually nothing but you using the chain rule to calculate all the derivatives of the parameters theta as you move back in the network. And one of the reasons why you often start at the endpoint when you calculate the derivative, because when you do the back propagation, you could have actually started calculating the derivatives here. But normally the output here is normally much, much smaller than the input here. So if you have an image with 200 pixels, you would have 200 nodes for every image, but your output is just either 0, 1. So the dimensionality there is much smaller, and then you just propagate backward. So the back propagation algorithm, the famous algorithm, is actually nothing but you using the chain rule. And this can then be automatized with automatic derivation. And you have several functions and libraries which do that for you. Now, when you then do a neural network, what we have done then is that the input data is now encoded in terms of an initial state. So the input data, which we have, is now encoded, and this is the part which we discussed last week, into a state, a quantum state, which we are going just to label as a psi of I. So this psi of I, when we think of it, this is just going to be given by some unitary set of unitary transformations. And what we want at the end is to calculate an expectation value. So the quantity f of I, which we have of theta, is going to be defined by a quantum mechanical expectation value, where we now have all these unitary transformations which we have performed. And last time we discussed the calculation of this kernel, which was then given by the angle embedding. And then we have the adjoint of that one, which is the other. And if we have this operator, so this operator is now the one which represents the quantity we want to calculate. So this operator here could be the expectation value of the Pauli Z matrix, just to give you an example. And then you would have a U of all these angles theta and multiplied with this psi of I. So a typical convention which is used when you set up a quantum neural network is that you let these operators, or this set of angles theta. So the angle theta, or the angles theta, we could say the parameters theta, they are typically set up so that the operators actually affect only a single gate. And you could now think of having n quantum registers with L layers. So this theta which you have now, if we now set it up as a matrix, you could now have a theta 1, 1, a theta 1, 2, to a theta 1 L, where L is the given layer which we have. So this is the columns here, represent the layers of a neural network. Then we will have a set of quantum registers where we encode this information. So these are the qubits which we then operate on with a single qubit rotation on each one. So that means that we would have a theta 2, 1, and down to the final register, N1. And this goes all the way to theta N of L. And typically this matrix is now a matrix which has complex entries, and it has a dimensionality of N times L. So we would then use something like N qubits, so we often call them registers, and we have L layers of adjustable quantum gates. And where each gate is controlled by a single parameter. So that means that if you now think of each single gate, this would be something like a gate operation where you now could think of one of these registers with parameter theta ij. And this gate operation is something which we would call G of theta ij. And the typical way this is done is that this is one of these gates or rotation matrices, Rx, Y, Z, where we have a function of some angle, theta ij. And this is then multiplied with one of the Pauli matrices, which we can just write as a XYZ here. So that's we are coming back to the explicit form of these types of gates. So what happens then, if we now look at this operator U, the generic form U of theta. So I'm going to write this in a little bit more compact way. So what you could think of now, when we now single out the specific one, is that there is a set of gate sequences that comes after that specific layer. So we have a G of theta ij, and then we have a set of operations which precede that specific layer and that specific register. So you could say now that this is a gate sequence. So you see quickly that when you're running quantum neural networks, you're going to have quite many gates. And what is normally done then, as we discussed last time as well, since in this NISQ era of quantum computers, if we have too many such gate operations, it's not given that actually the quantum computer will be able to handle a large data set. So you would often then try to use, for instance, a principal component analysis on your data and reduce the dimensionality of your data set. And you will see that typically all this kind of calculations which have been performed till nowadays, when you take a data set like the MNIST data set, which is just this set of 60,000 images, this is often just narrowed down to numbers 0 and 1. So you reduce the whole data set and you blur also the pictures. Instead of having 28 times 28 pixels, you reduce it to 8 times 8 pixels, which means that you would have 64 input nodes. And then if you just have 2 images, you have a typically binary classification problem. And this will be the typical calculations which have been run on an actual quantum computer nowadays. Because you see quickly that if you have many such registers, N as we call them, and you have many such gate operations, this clearly becomes a long, long chain of operations. So these are gate sequence. So V or W precedes this G theta J, theta IJ, and V comes after. So the way you could think of this now, if we now go back to that image which we had in the lectures here, so let's just go back to the Jupyter notebook. So if we now look at the material for this week, you could now think us having nailed down this specific one. And then you would have a chain of gate operations before this specific one. And then you have a new chain of operations after that one. So each one of these parameters theta are a parameter to which we need to calculate the gradient of. Now, to calculate the gradient of these quantities, we end up with the same trick which we had for the VQE, which we call the parameter shift rule. So let me just give you the basic mathematics behind that, because then you see how we can set up the gradients. Because the gradients will be calculated by the classical computer. But quantum mechanically, we are going to set up all the operations which you see here, and then we produce a final measurement. This bit string with all the parameters is then returned to the classical computer, which then updates the gradients. Then we have new parameters for the angles, and then we repeat this till the gradients, or this cost function which we have defined, reach a limit value which we are happy with. So let's go back to the Jupyter notebook. No, sorry, to the whiteboard, and let's look at the details of these derivatives. So what we can do now when we are looking at the specific expectation value, so the function which we want to evaluate, this is our model, is now given by the expectation value of some operator, which we haven't defined here yet. But this could be a poly-Z gate. Exactly as we did it with the VQE. So if you think in terms of the VQE, what we are doing here is not that different. So in order to find the derivatives with respect to this parameter, I'm just going to rewrite a little bit the equations. So I'm just going to introduce an intermediate operator. So these are Hermitian operators, all of them. And so I'm going to just define a new operator, which I call for Q, which is going to be this collection of gates times the operator we want to calculate the expectation value of, NV. And then I'm going to take that set of gates, W, which I have here. These are going to act on the initial state, which I have prepared. So the initial state could just be your system being prepared as a tensor product of bit 0. So if you have 2 qubits, this is just 0, 0. If you have 3 qubits, it could be the tensor product of 0 with 0 and 0, and so on. So that means that when you now look at these equations, I'm going to redefine a new vector here, or new state, which is now the preceding operations acting on this initial state. Now it's you, if you want to give a lot of flexibility. So you don't know how deep the network should be and what kind of gates are the optimal one. So this is often done by a lot of trial and error. So you can make these operations as complex as you want with the C0 gate or CX gates and lots of rotation gates. And then when you have that, if we now look at the final quantity, so the derivative which we want is actually the derivative of this function f of I as a function of theta with respect to one of these guys, theta j. So what we want then is actually to calculate d of d theta ij. And what we are going to have then is an expression which is going to look like as follows. So we are rewriting this expectation value, which means that there's going to be now a state phi of I, which now contains the preceding operations. Then I have my gate operation, G, complex conjugate, and then I have this operator Q, which I defined here, which now contains V, Hermitian transpose times O times V. And this is then multiplied with G of theta ij. So there is a theta ij dependence here as well. And this is again multiplied with phi of I. So this is a quantity whose derivative I want to calculate. This is nothing but what we did in the VQE and project 1, except that then this was just the expectation value of the Hamiltonian. And the trial wave function which we had was given by Hadamard gates, rotation gates, and also control X, so control Y and control Z gates, which then could be encoded in this W times this here. So what you see here is actually us rewriting this expectation value, which then defines the function, or in this case of a classification problem, it could be a bit string, which follows from the number of times we measure, let's say 0, 0, 1, 1, 0, 1, 1, 0, if we have 2 qubits. Does that sound clear? Okay, so when you set up these equations here, we can now repeat the same trick which we used when we set up the parameter shift rule in order to calculate the gradients of the Hamiltonian in the VQE, but now we need the gradient of this specific expectation value. So what that means when we now do the derivatives is that we will have an expression here. So this becomes equal to the state phi of I. And then I have my d of d theta ij. I'm just setting up the standard rules for the derivatives. And this acts on this operator Q. And then I have my g of theta ij and phi of I plus, and then I have my phi of I, or my g. So this should be this quantity here. Hopefully I'm writing this off correctly, multiplied with this operator Q, and then I have my derivative of d of theta ij of g of theta ij and phi of I. Then what you can do then is just to introduce new variables where I use b equal g of theta ij. So I'm just repeating the same old trick which we used when we did the variational quantum eigensolver. So this is the kind of repetition which we are also doing since this is the last lecture. So I'm just reminding you of some of the basic quantities. And if we do that, so we use now the same trick because we can actually rewrite this quantity when I introduce these shorthands. I can actually rewrite these quantities as a phi of I, and then I have this C dagger, and then I have my operator Q, I have my B of phi of I, plus phi of I of B dagger, and then I have Q of C of phi of I. And this is something I can actually rewrite in terms of a new sum of operators, which then allowed us to introduce this parameter shift rule. So this quantity which you see here, this is something which I can rewrite in terms of 1/2. And then I have my phi of I. I have my B plus C. It's actually, if you write it out, you will see that this is correct. And then I have B plus C of phi of I. And then I have an additional term where we obviously have to have B minus C in order for this one to become the same as the previous one. So there's a minus here, So let's put that up. So there's a minus, and then I have phi of I of B minus C dagger of Q of B minus C of phi of I. And then when we use this parameter shift rule, we end up with analytical expressions for the gradients. So let's just remind ourselves of that. So I'm not going to rederive it because we did that in the derivation of the derivative of the expectation value of the Hamiltonian in the VQE calculation. So you see also that this becomes quite complicated because if we have hundreds of such angles, we need actually to calculate hundreds of such derivatives. And each one of them is going to give us an element in the back propagation algorithm for the classical neural network. So the only thing which we are doing here compared to a standard neural network is that instead of having the gates with the weights, etc., not the gates, but the weights and the biases, we are now replacing everything with a kind of kernel functions as we discussed with quantum supervector machines as well. So when I do that, the other thing which we need to just remind ourselves of is that these operations G of theta ij is typically given by a unitary gate operation, which is now given by some exponential of minus I of theta ij, and I have a gamma here, and gamma is a Hermitian operator, which in our case is just given by the Pauli matrices. So in our case, this Hermitian operator gamma, so gamma is a Hermitian operator, is just going to be sigma x, sigma y, sigma c, and also we have the identity matrix. And this is something which we did before. And when this operator gamma has only two eigenvalues, we can actually add an arbitrary phase. So that means that we can then set up a very simple derivation of this function, which is now given in terms of the following. So I'm skipping some steps because we did that in the derivation of the parameter shift rule for the VQE ansatz. What we end up with then is now to have an expression which runs like R divided by 2. So R is a shift which we add, and this R is the eigenvalue of the Pauli matrices. And we have only two eigenvalues, either plus or minus R. If you think of the Pauli Z matrix, it has eigenvalues -1 and +1. So this R is actually the eigenvalue of one of the Pauli matrices. And then we have a phi of I. And when you then expand the exponential of your operator G, then this would be given by -1 over R. And then I have this Hermitian operator gamma, which is actually one of the Pauli matrices. This is complex conjugate multiplied with this operator Q. This is then multiplied with the identity minus I divided by R times gamma, and then it's multiplied with phi of I. And then I have an additional sum. And let me set up that one, not an additional sum, but an additional term. So I'm just setting up the terms which we derived previously. So I get a phi of I. And now I have a identity plus I divided by this eigenvalue of this matrices gamma. Sorry, not that way. I just wanted to set them up so that we have everything before we take a break. And then we have complex conjugate of Q, Y plus I divided by R of gamma multiplied with phi of I. And that terminates the expressions here. Now, if I now introduce a quantity S, which is pi divided by 4 times R, and the R is in our case for the Pauli matrices is actually ±1/2. So what I can show then, and this is the kind of element of repetition where we use the same result we had with the VQE. I get R multiplied with phi of I, and then I have this G, and now this is calculated as a function of theta ij plus this variable S multiplied with Q, and this is multiplied with G of theta ij plus S and phi of I. And then comes the next term, which is minus, and then I have my phi of I, and then G of theta ij minus S multiplied with Q of G of theta ij minus S. And this is then finally taken with that specific state. And it means that this value, which we have here, this quantity, due to this means that S is actually equal to pi half, and we will have plus minus pi half. So the phase shift rule, or no, the parameter shift rule, means that we have an analytical expression for the gradients of d theta ij, which is then equal to 1/2. This is the expression which we actually encoded in the VQE. So then I have a G of theta ij plus pi half multiplied with Q, that operator, and then we have G of theta ij plus pi half of phi of I minus, and then I have my phi of I of G dagger theta ij minus pi half of Q multiplied with G of theta ij minus pi half. And finally, this is multiplied with phi of I, like this, and final parenthesis here. So we need to estimate then the gradient by executing two circuits n times. So if n, uppercase letter n, is the number of shots which we perform, so we would actually need to execute the circuit. So this would be one circuit, and this would be the other one. And we need to execute that one n times by doing two circuits. And then we would collect the statistics. And when we collect the statistics, we get the final result for f of I here. This is then fed back into the cost function, and then we keep iterating this one again and again till the cost function stabilizes and gives us a as good as possible fit to the data. So the QNS can then be trained with a gradient descent algorithm in full analogy with what you do in a standard neural network. So I hope you see the overarching picture. So this will be the technicalities which we need to implement in a parameterized quantum circuit, but where we now have, in principle, many more gates, because we have the gates which are included in here, the gates which transform this state till we have reached this one. So for each one of these variables, we need to apply this parameter shift rule, and then we will have analytical expressions for the gradients, as we did with the VQE. Now, you could say that, why don't you use a finite difference? Now, the finite difference is very sensitive to your step size. And since you're dealing with quantum computers, there is a limit to what kind of step size you can use before the resolution is too bad, which means that a finite difference, which in principle is very straightforward to implement, can actually lead to a precision which is much lower. And you remember from the VQE, I don't know if you did test it, but some people did that in project number 1. They did test a standard finite difference calculation with the analytical derivatives. So as long as these gates, which we are dealing with, if we go back to the expressions which you have here, so as long as these gammas here are given by the standard Pauli matrices and they have only 2 eigenvalues, then this parameter shift rule is actually easy to implement. And typically, when we are setting up and we take a small break soon, I just wanted to bring up the circuit here, which we have. So when we are setting up this circuit here, the most common approach is actually to only vary the parameters of the rotation gates and leave the control gates unchanged and fixed from the beginning. So you could think of that almost as a hyperparameter which you use in a standard neural network. So a standard neural network, you update the weights and the biases, but you keep the number of nodes fixed, the number of layers fixed, and you would also have a learning rate and the other hyperparameters fixed. So this is something which is often done because it also simplifies the calculations. But the complexity of the problem is something you can play around with, as you do with a neural network. So a standard neural network is defined by the gain, the number of weights and biases, hidden layers, and number of nodes. And these are the parameters which define the model. So the architecture of a neural network is your model. In our case, you can think of this figure which you see here as a neural network, but where now the operations are replaced by operations on quantum mechanical states. The classical input is transformed into a quantum state, this state psi of k, and then it gets propagated by actions on each individual qubit. And after that, we end up with a measurement, and that measurement is then fed back to the gradient descent algorithm, and the gradient descent updates the parameters, and then you go back and forth till you reach your convergence. Did that help a little bit in seeing what happens in a neural network, a quantum neural network? Hopefully. So let's take a small break. And then after the break, I wanted to go into a little bit the calculations and how we can actually set up a quantum neural network. And then when we are done with that, I hope I can say something a little bit about Boltzmann machines, because these are generative methods. The only problem with Boltzmann machines is that it requires that you also have some knowledge in order to appreciate the full beauty of them, of both statistical mechanics and quantum statistical mechanics. So I will try to give you some of the basic ingredients after the break. But the first thing we will do is actually to discuss a little bit the way you could encode a quantum neural network with a software like PennyLane. So if we now go back to the slides from last week and take a closer look at how we can implement a quantum neural network. So you will see now much of the same information which we discussed before. So we have this U, which acts on an initial state, which is then just a tensor product of all these bits which we have. So it could be all zeros. So if we have a 2-qubit case, this would be just 0, 0. And then we act with this U of x, which now is just a set of unitaries, rotational matrices. So this is just composed of rotations. And that depends also on the data which we have. As we discussed last week, the typical way which you embed the classical data is by letting the angles represent the given features of your data. So last week we looked at this credit card example, and then we needed 3 angles to encode age, income, and the sex of a credit card holder, just to give you an example. And then we had some further operations, and what we want to do is actually to calculate, as we said before the break, is to calculate this expectation value. And that gives us this function, which we call f of I, and that depends on the angle theta and the let me just bring that one down. And with that one, we have now the function, and we need simply now to find one way to encode this information. And this is essentially just a quick reminder. And this is normally called a variational quantum circuit. It's a quantum circuit with trainable parameters acting on a quantum state. And it is central to basically all these kind of near-term methods. Let me just switch off this one, so I don't have that. Sorry for that, small intermezzo here. So these simple encodings normally use rotations on each qubit, and while more complex feature maps may also include entanglement. And as I said, a pretty common procedure is to let these entangled states just be fixed by an angle when we run through the calculations. So the only parameters which we train in the network are those which deal with a single qubit operations. So I put in some exercises here. Just compute the state for 1 qubit circuit, and so you define an Rx and then an Ry as a function of theta, and then calculate the expectation value of Z. This is actually what you did in the VQE implementation. So it's not that different. So the quantum neural network then, so we would have this input coding, we would have the basis encoding. This quite standard one is this angle encoding we discussed last time. We also have an amplitude encoding, and there's also something which is called data reuploading. But the most common one is often to use the angle encoding. And then we use rotation gates to encode real values like this. So typically what we have is classical data. That's the kind of situation we have limited ourselves to. So we are not using at the case where the data you're feeding in is data from, let's say, a quantum simulation. So now we will typically have a set of, let's say, Van Gogh paintings, and then we want to classify or make a model which classifies new paintings and tells us whether this is a Van Gogh or not. So the typical architecture then is in terms of this parameterized set of unitaries. So we would embed, we have the embedding layer, and then we have a variational layers where we repeat L blocks of parameterized gates, and then we have the measurement part. So in the examples which follow here, we have a typical variational classifier. So I'm just going to set up the codes here. There's also a reminder here that the typical way we calculate these derivatives is by using the parameter shift rule. One of the problems we can have when we do these calculations is so-called barren plateaus. Are you familiar with that from? So there is a well-known problem in machine learning, classical and quantum machine learning. And that has to do with the fact that the gradients in the training can sometimes become zero or become very small. And that means that when you do the gradient descent update, the update of the parameters barely moves. And sometimes the parameters can run to zero, and then the training stops because your neural network is actually you applying the back propagation back and forth. And at the end, what you're evaluating is your cost function. And that's the one, if you're dealing with a mean square error, which you want to drive to zero. You are not necessarily interested in driving the gradients to zero. So the gradients are part of the training, and you update the parameters back and forth through the back propagation algorithm, which means that sometimes the training can have gradients which go to zero or become very small. And then you reach a kind of plateau where your results just stay around a specific value and you barely move. So this is the problem of barren plateaus. And this is something you will find in, especially when you have deep neural networks, both classically and quantum mechanically.
Trying to push away.
Yeah. So there are several tricks. There's some, yeah. Go ahead.
No, sorry.
No, there are several tricks to avoid that. And one of these is actually to artificially just change the parameters so that you move away from this barren plateau. So this is actually a problem which is not only pertinent to the quantum case, but it applies to the classical case as well. And it's a big problem in training of deep learning methods, especially if the networks become very, very deep. And I guess that some of you have been working with machine learning methods, and you probably encountered the topic of barren plateaus. So that's a classical problem. So there are some exercises as well, but when you do this with penny lane, the typical way, which we will do that now, in this case, it's just a 2-qubit example, and we discussed that partly last time. And in this specific case, you would now define your device with 2 qubits, and then you have a feature map where you encode the data, and so you perform a rotation on one of them and a rotation on the next of them. And then by these rotations here, you can also set up a parameterized quantum circuit where you also have a C0 gate. And when you have that, you can then afterwards set up your classifier. So you have the variational layers, you set up the number of the layers you want to do then, and then you calculate the expectation value of a Pauli Z gate on qubit 0, exactly as you did in the variational quantum eigensolver. And the examples which follow down here, one of these is just a simple vanilla set of data. And the other one which follows down here, I'm just going to scroll down a little bit, is actually one on credit card classification, which is the same which we discussed for quantum support vector machines last week. And this is just a synthetic data set which contains features like income, debt ratio, and age. And then we label each data point as good or bad, credit. And depending on, so this is just a fake data set which we are making. So in this case, we would have 100 data points, and then we set up just the income, debt ratio, and age by just random numbers, as you can see here. So this defines your input. And then we have a simple linear rule with some noise, which defines, so 1 is good credit and 0 is bad credit. And these are the data which we want to train. And you can see again that we use the standard libraries like scikit-learn and set up data into train and test. And then we set up max income, max depth, and min age and max age, and then scale the data. So this is all, this part here is just the classical pre-processing. And then when you've done the classical pre-processing, you can transform this by angle embedding into your quantum representation of the classical data. And this follows very much the same procedure which we discussed last week in connection with quantum support vector machines. So as we mentioned, I mean, there's a classical part, and everything you see here is just the classical part. And you could obviously run this with a classical part. But here we define a variational quantum circuit with 3 qubits, because we have, in this specific case, we have 3 features, and we let each qubit encode one of the features. So that's one way of doing it, by the angles which you set up. And then we do the angle embedding, as you can see here, and that is now given by a rotation around the y-axis. And this contains also an entangling layer. So this gives more complexity to your quantum layers. And then, so this just returns to your circuit. And then you define just one hidden layer. You initialize the weights. And then finally, we do a cross entropy loss. This is your loss function, which then returns simply by the gradient. So there is also a function here, which is called gradient descent optimizer. So this is the classical one. You would actually be able to run this quantum part on a quantum computer. But in this case, we're just running it on a classical one. The cross entropy is your loss function. So we're simply calculating the logs here, or the probabilities. So the quantum part returns the probabilities. We run this for a given number of shots. And I think in this case here, we defined something like, what was it? I don't remember where I put the number of shots here. Somewhere there is a number of shots here. I just have to look it up again. But you will repeat these experiments and you simply count the number of times a given state appears, and that is your measurement. And then the one with the most counts is the one which is the most likely outcome, and that is your probability. So this would be a typical example on how you would encode a quantum neural network, and then you do the training in terms of the number of epochs, etc. And this is the number of iterations back and forth. And the accuracy and the precision is what you get here. And it's not actually that impressive, but it's okay.
Outcomes that are appear almost equally often.
Yeah.
Then you have a problem.
Then you have a problem. Yeah. Exactly.
Then you have to use maybe classical statistics to sort of decide.
Yeah.
How you have to run.
Yeah.
To distinguish which one is.
So what many people do is that they take the quantum output and just save that to file, the number of counts you have, and then you would use classical statistics and do the analysis. So that is pretty cool. So the post-analysis would typically be done with classical methods. Okay. So this is a typical example on how this is one of the simpler cases there. Actually, this is a very broad research field, and there's a lot of interest going on in quantum machine learning, is particularly in finance. This is a field where many people are actually studying quantum machine learning algorithms. So one of the things which I wanted to say a little bit about, if we get time, without abusing too much in your patience, is a little bit about quantum Boltzmann machines and Boltzmann machines in general. Are you familiar with Boltzmann machines? Now, Boltzmann machines is a very popular machine learning method, deep learning method. They are methods which allow us to generate a probability distribution. So when I use a neural network as a discriminative method, it means that I'm training on, like the example we did, either with the credit card debt or the Van Gogh images. And I make a model which allows me to discriminate between whether this painting is a Van Gogh or not, or whether this person will pay credit card debt or not, or just default on a debt or not. So that will be typical examples of what we call discriminative methods. So a discriminative method is one of the really standard machine learning methods, which means that you're interested in essentially two things. One, to make a prediction. You train a model, and you want to apply that to data which has not been included in the training. And secondly, you're often interested in finding correlations in the data set. So suppose now you look at this credit card data, you would like to find a correlation between whether this person defaults on the credit card debt or not by looking at features like age, education, income, etc., etc. And then you would find correlations among these features, and some of them can be strongly correlated and some of them can be less correlated. So it's pretty obvious that if you set up the correlation matrix, you will find a strong correlation between income and whether you default or not on your credit card debt. That sounds, and if you are a student, it's probably more likely that you will default on your debt compared to somebody who's not a student and has a permanent job. So some of these correlations are intuitive and obvious, other ones are less, and this is what you would typically do in a standard machine learning context. Now, generative methods are, however, from my point of view, the more interesting ones. Because at generative methods, you train a probability distribution. With a probability distribution, you can make predictions. I can generate new data. I can find correlations in the data. I can set up my correlation matrix, obviously. I can calculate the variance. I can calculate the error on the parameters. So I can find out standard deviations. And I can say that my model gives this and this prediction with this error estimate. But then it comes with more. It tells you also about causation. What is the likelihood of A given B? So normally the standard machine learning algorithms, they often fall into a slot in statistics, which is called a frequentist approach. So you're more interested in the frequency of the data and perhaps less interested in getting a probability distribution. If you go into the Bayesian way of thinking, you're then interested in deriving a probability distribution. So when I do science, my kind of science, the probability distribution is actually the interesting quantity. Now, if you look at many of these ChatGPT algorithms for making images, and probably you have used a software called DALL-E from OpenAI, that's based on diffusion models, which are generative models where you actually train probabilities to reproduce the data. So that means you train on images of horses, and then you ask your final model to make an image of a new horse. You want a white horse with 5 legs, for instance, right? So these models have become fantastic, and you probably, when you use DALL-E, like one thing I did just some days ago was to ask it to make a picture, an image of a valley in the Dolomites. And it was really realistic and really good. So Boltzmann machines, if we now go back to what we have here. So if we scroll down, Boltzmann machines are actually models which start with a Boltzmann distribution. So what you assume first is that your variables are to be considered as independent and identically distributed. So what you want then is to train that probability distribution for some given stochastic variables. And clearly that is a maximization problem because we want to maximize the probability. There is no interest in what is zero probability, right? So when we look at the optimization part, instead of minimizing like the mean squared error, which we did with the neural network, now we want to maximize the probability. And typically this Boltzmann machine has some hidden layers. So there is a hidden layer, and that connects with what's called the visible layer. So the way you could think of it, of a Boltzmann machine, if we now go back to the Jupyter notebook, no, sorry, not the Jupyter notebook, but the whiteboard. So it's a sign that I'm getting close to the end of the semester since I always confuse Jupyter notebook with whiteboards. So if we now look at these typical probabilities with a Boltzmann machine, so you have a function, a probability, of given in a state xi, which is given by some function of x, and now this has a parameter theta. So there's an x of I, and this function, we are leaving that undefined till now. And there are some parameters theta. So what we want to do then, and there's a normalization factor, z of theta. So this is nothing but a standard probability distribution where we have a normalization factor, which is this quantity here. So this is just a normalization constant. And the rest of the function, which then defines the probabilities, is given by the function which we see here. So this could be a Gaussian, for instance. It could just be e to the minus x of I, and then squared, and so parameters. Now, the total probability which we are interested in is some p of theta of x, which we would typically write as a product of all the individual ones, where the x of i's now belong to a domain of events of p of x of I of theta. Now, we would call this the marginal probability, but we could have a probability now which depends on additional parameters of x of I of h of I, and this h of I could be our hidden layers, which belong to the training. So what we normally do then is that we want the marginal probability, which is this p theta of x of I, which is typically now a sum over the h of i's which are now defined in a domain H, and over the p theta of x of I of h of I. So you could think of you having a probability for being in a two-dimensional space with the variables x and y, and then you want to reduce this to be the probability of being along the x-axis. So that means you would integrate away the y-axis as degree of freedom, and then you would have the marginal probability. So in this way, you have now a model which is defined by this function f, and also this normalization constant. Now, this normalization constant is the ugly beast. So the z of theta is actually u summing over all the x of i's in a domain D, and all the, did I use D here? Yeah, I used D. And then the h of j in a domain H. And then we will have simply these probabilities of x, no, not that one, but the function f of x of I, of h of j, and parameter theta. Now, the reason why these are called Boltzmann machines is that you're inspired by the Boltzmann distribution. And in the Boltzmann distribution, this function f is something which is given typically in physics as the energy of the system. And that's why these are also called energy-based models. So if we now think of the standard ways by which this has been done in physics, you could now make a model for this x of I, x of j, of theta. And now theta is going to be a container for a set of parameters where I have a vector A, a vector B, and a matrix W, where this one could now be given by a sum over all the visible nodes. So we have n visible nodes, and I have some parameter A of I multiplied with x of, now I should be a little bit careful now because I used x. I should actually put in just a generic x here and h. So these are vectors. So they contain all the possible variables. And then you can nail it down to a specific one. And then you would have a sum over j equal 1 up to the hidden nodes. And this B's and A's, they play the roles of so-called biases in a standard neural network, plus the weights which now link these two and m, and then we have these parameters wij with x of I and h of j. And the way you can think of this now is that you have a network which looks as follows. So you have... Yeah. Yeah, that brings in correlations between the visible layer and the hidden layer. So the way you can think of this now is that you have a visible layer like that. So we'd have x1, x2, etc., up to some xn. And then we have a given number of hidden nodes where we end up with hm. Then you have h1, h2. Now, in these Boltzmann machines, historically, you also had connections between the different nodes in a given layer, but that gave models which were difficult to train. So that's why one abandoned these additional parameters and simply looks at the connections here. So that will be W11, W12, W13, etc. And then you would have similar ones here connecting this one with that one, etc. So this is then reflected in this model, and you could then decide whether you want this model to be a binary one. So the binary one is a case where x and h, so this is a binary model. So that means that x of I would now take values like -1 and +1. or 0 and 1. It's up to you how you define it. And you could have the same with h of j, which is -1 plus 1. So you see now that what you have is a model which is going to be trained so that you optimize this probability distribution, because at the end, what you want to do is to find the optimal theta, which is an argmax of all the values of theta, of these theta values, and you would then optimize the probability for all the x's which you have. So this is a quantity you want to optimize. So we want to optimize the marginal probability. These Boltzmann machines are interesting when you have these simpler types of ansatzes, because you can actually set up these probabilities when you have a binary-binary. I could replace a binary-binary with a binary Gaussian, because this function here, I should actually say, I actually did something wrong here. I forgot that. So this is, I should rewrite this one. This is given by the exponential of this function, xi, hj, and theta. So that's the Boltzmann distribution when we follow that. Now, if you have a binary-binary, you can replace it with a Gaussian binary. So that means that in that case, this would be an x squared, which then would lead to a Gaussian part. And then you would have one part here, which would then just reflect the binary part. So you can change the type of Boltzmann machine or Boltzmann function, and then try and see which one gives you the best reproduction of data. Now, nowadays, in classical Boltzmann machines, what people do is that they replace this function with a neural network. And this has proven to be extremely efficient. So people have replaced this function with a neural network. They have replaced it with a convolutional neural network for imaging, etc., etc. So these Boltzmann machines actually were introduced for imaging back in the beginning of this millennium. But then they lost a lot of the steam because they were difficult to train. And then in 2010, I mean, convolutional neural networks hit the market, and they just wiped out all competitors. So, but these Boltzmann machines have gotten a revival classically. And the way you train it now is a little bit tricky. And I'm going to set up some of the basic details by going back to the slides. So I wanted to bring this up because, as you can see here, it looks like a neural network. So what we need to do then, since we have a probability, we are not going to calculate the derivatives of a product here, but we are going to take the log of the probability. And this is what we will be training. So in the training, what we actually set up then is a theta is argmax of theta of log of p theta of x. So this is a problem which is easier to handle because our probability, the model which we make, is a product of all individual probabilities. This is much more difficult to calculate the gradient of, which in turns means that if we replace it with this problem, which is fully equivalent, then we have an easier optimization problem. And this is essentially what is done. But now I wanted to give you some more technical details because they are going to link with the setup of a quantum Boltzmann machine. So quantum Boltzmann machines have become extremely popular because they also belong to this class of generative models. And we can set up a variational quantum circuit like we did with a neural network with the same type of rotation matrices, etc., except that now the thing we are going to optimize is somewhat different. So let me try to give you the basic mathematics by looking at the classical Boltzmann machine, because hopefully that will give you the flair of these methods and why they are tricky to actually train. There's a reason why they are tricky to train, because the ugly part or the nasty part lies here. So just think of you having a binary case. And if I have 100 visible nodes and 100 hidden nodes, then this sum here will run over 2 to the power of 100. And this sum will run to 2 over power of 100 configurations. So to calculate this normalization factor, which in statistical mechanics is called the partition function, is a very difficult topic.
Raised so 2 to the 100, the 1000 raised to the 10.
Yeah, even with 100 nodes, which is a small case. So if I have, let's say I want to train an image with 200 pixels, I would then need 200 input nodes. And if I have a binary case, then it's 2 to the power of 200. So that would be the possible number of X values. And you see that classically, this becomes very tricky. Quantum mechanically, on the other hand, you can actually reach this dimensionality. But let's see how it's done classically, because that's the way it's also done quantum mechanically, except that this probability takes a slightly different form. So maybe we just end up with a classical case. So let me just show you that, and then you can have that as a fun read when the semester is over. So we'll probably not get the time to go through all the gritty-nitty details. But this is, so we have a function here. So this function here is now the sum here. And a typical, if we now just scroll down a little bit, because we went through some of this in the slides. So the problem resides in us calculating this normalization constant. So the way you actually do this as an optimization problem is now to, if we now look at these products which we have, this is now going to be given by this equation here. So this is just a rewrite of what we had on the whiteboard. This now has the, this is just a constant, the partition function, which you see here. Keep that in mind, that is a normalization constant, but it will depend on the parameters we have, because the partition function is now given as a sum over the variables, the hidden and the visible ones, but it has a function dependence on theta. And this will be the parameters of the quantum neural network or the classical neural network for a Boltzmann machine. So when you do this, the way we would optimize the problem is to take the log of the probability. So this is the optimization problem. And this is the quantity we want to calculate. Now, to calculate that one means that we need the derivative of the normalization constant. And we want to avoid to calculate that one. So how do we do that? So there is a trick which leads to something which is called contrastive optimization. Because when I take the log of this quantity, if we go back to the expression, so the log of this function is going to have this term with a minus sign and the product, which is a sum. Now here we have a function for it, which we have defined. So you saw before when I was on the whiteboard, I had a simple mathematical expression for it, which defines my model. And you can actually replace that function I put with a neural network or convolution neural network. The only difference then is that everything has to be done numerically, because with this binary case I mentioned, I can actually set up analytical expression for everything. So what you end up in the optimization is to calculate these two terms. Now, this one is something you can evaluate because you have a model for that function. So the difficult part is this one. So the question is, how do we handle that one? So the way you handle this one is actually through Markov chain Monte Carlo calculations. So this is something we will rewrite as a statistical expectation value. And that's the way you calculate it. So this is normally called a positive phase, and this is a negative phase. It's called contrastive optimization because you have these two terms which will contrast each other. And for those of you who are more familiar with the statistics, you may have heard of something which is a measure for how good your probability is. It's called the Kullback-Leibler divergence, where you actually rephrase everything in terms of an expectation value, in terms of a known probability. And then if your probability is approaching the correct one, then this Kullback-Leibler function is exactly equal to 0. But this is a technicality which we will leave a little bit. But the interesting thing for us now, if we look at this expression, so this theta of log of c is actually the function which we have times the derivative of log of c, because what I'm setting up here is now simply my definition of the partition function, which is this one. So when I take the derivative of the log of this one, I have the function, I have the log of the function, and then I end up with an expression which looks like that. So this is the expectation value of log f, if you look at this one. So that means that the derivative respect to the parameters of log c is actually the derivative, because this one divided by that one is my probability. So this is nothing but my stochastic expectation value. So this is something you would calculate with Monte Carlo sampling, and you would use Gibbs sampling as the standard sampling rule, because that's much more efficient than metropolis sampling. So this is a technicality. Then I have some further technicalities here, but we would just leave them out here a little bit. But the typical model which you would have for this function here, so this should actually be the exponential. Sorry, I'm actually missing the exponential here. But you could this is the one which I put on the whiteboard. So this is actually what you end up with in a vector form. So the derivatives which you need are actually easy to calculate, because you would simply have to take the derivatives of that function. And that means that you need the derivative with respect to the weights. So that means you take the derivative of that quantity. You have the derivative with respect to the bias A of I, which is a derivative here. So with this kind of model, the so-called binary, you have simple expressions for the derivatives. So when you're training the model and you need the gradients, many of the expressions are pretty easy to set up. So what I have here is actually a link to more details, because I'm also teaching a course on advanced machine learning. And I actually spend 6 hours on Boltzmann machines and discussing the codes. So I'm just giving you the overarching view on it. I hope you can forgive me for that. There's also a code example where I train on the MNIST data. And in this specific case, I use a binary Boltzmann machine. So I train on the data. It's actually going to be a little bit slow here. But now it's downloading the MNIST data. But you can see an example on the kind of training which is being done and how well it reproduces. So this MNIST data is a set of handwritten numbers from 0 to 9. So it's 10 classes. So in the beginning, the reconstruction error is pretty large. But you will see then from an image that number 8 actually, which I produce with my probability, actually looks like a number 8. So Boltzmann machines now have gotten a revival, because this function, this energy function, is normally now replaced by a deep neural network. And that is much heavier to train than the simple case, because here in that code, I have simply implemented a binary Boltzmann machine, which has analytical probabilities and analytical derivatives, which makes it much simpler. But you can see now the final reconstruction of one of the images. I just picked one of them. I think last time I run it, it was number 8. It doesn't need, I think now I'm actually looking at number 8 here. So let's just see what happens. It should come pretty soon. Yeah, so you can see the original image, which I fed in, and the reconstruction. It's not so bad. So these models, I mean, I don't know if you use some of this kind of image generative method just some 5 to 10 years ago. When you wanted it to make an image of a horse, you could get a horse with 5 legs, or 2 tails, or 2 heads, or whatever. But now they've gotten so good that when you run DALL-E on ChatGPT, you really get fantastic images. So I'm actually tempted to make some of the images I've made for the lectures, to actually ask ChatGPT, make an image of a neural network. Anyway, I'm going to quickly stop here, but there is in the quantum Boltzmann machine, the state we are going to train is actually, now we need some information about quantum statistical mechanics. And in that case, this row here is the density matrix. And you can show that your partition function then is actually given by the trace of the density matrix. So the partition function is actually the trace of this exponential. So beta is normally set to is inverse temperature set to 1. And this h is this function which we called f in the notes above. So this would be typically be the energy function. And now this partition function has a slightly different meaning. And when you're calculating expectation values, we are going to train now a function which is the density matrix times this observable. So I've put in some more mathematical details. Many of the types of models which we deal with look alike, like the restricted quantum Boltzmann machine, except that now, instead of training a probability, we are going to train the density operator, which represents a way to represent a specific state. So I'm going to leave this as something to look at after, because our time is over now. And I just wanted to point to the Boltzmann machines, because that's a very interesting model for generative quantum machine learning methods. And there are many people studying Boltzmann machines with applications to, let's say, simulations of financial data. So there's a lot of interest in applying machine learning methods and quantum machine learning methods to finance. And I know many groups and many banks. Actually, the Norwegian bank with its investment fund is very much interested in discussing and learning about quantum machine learning methods. You have these investment funds in different parts of the world, like the one in Dubai, has even invested in the development of their own quantum computers. So there's a lot of activity going on here. And hopefully, this also discussing the parameterized quantum circuits in connection with machine learning brings back some of the things which we discussed in connection with the VQE, because that is also a parameterized quantum circuit. So in this era, this NISQ era of the near intermediate quantum computing stage, which we are in now, where you have a lot of noise and many of the gates suffer from both noise, decoherence, etc. Then having short circuits plays a very important role. And algorithms of the hybrid type, where you run parts of it, you use superposition, quantum mechanical interference, and entanglement to reach a much richer representation of data. And then in the optimization of the parameters, in these parameterized quantum circuits, you use a hybrid approach where the gradients are typically optimized classically. And then you go back and forth between a classical optimization part and the quantum part, which is then hopefully the one which gives you all the richness of quantum mechanical approaches. There is a lot of research on linear algebra methods running on quantum computers, but the type of approach which people favor nowadays is actually this hybrid approach. So if you go back to like the quantum phase estimation algorithm, one of the reasons why that was abandoned is simply because the circuits become too long. And the calculations become then, or the simulations on a quantum computer become intractable. So hopefully this course has given you a kind of flair of both quantum machine learning and the ways we can simulate eigenvalues and eigenvectors of a specific system, because they all have a common denominator. You're dealing with parameterized quantum circuits with a hybrid approach.